So we're up to lesson 5 for unit 4, and we're going to switch gears a little bit. We're going to look at 3 lessons in a row that are going to involve what we call max-min problems or optimization problems. And we're kind of going to do this just by on-the-job training, just one little page of theory here, and then we're just going to try out a whole bunch of different examples. And right off the start, I've just sort of mentioned that calculus is an excellent tool for finding best solutions to problems that allow for a wide range of similar solutions. And here we go. It's kind of about a 5-step process. We're going to try it out with example number 1 here, a story that you might have done from Math 11 where you were looking at parabolas and completing the square, but we're going to do it with a much simpler method in terms of finding the best solution. So the story says we're going to work with a rectangular plot of land, and it's bounded on one side by a river and the other 3 sides by a wire fence. And you've only got 168 meters of fence available, and they want to know what is the largest amount of area that you can actually enclose up against the river, and not only that, what are the dimensions of this little plot of land we're going to fence off with up against the river. So first step, when you can do it, I guess I should say, for these examples we're about to do, you can't always exactly do every single step, but you consider each one of these steps as you go through your questions. And first step here says draw an appropriate figure and label the quantities relevant to the problem. Often this step requires us to introduce 2 or more variables into the problem. Okay, all right, so here we go. I'm going to draw myself a little river here. All right, so there's my river full of water. And then I'm going to go and put a fence up against this river. And I've only got so much fence to play with. And I'm going to try to kind of draw myself out a rectangle like this. And I don't know exactly what kind of width I should go with. I guess that would be the same there, or what the length would be in order to fence off the most amount of area in here. Maybe I'm going to put some cattle in there or something, right? Okay, so step 1 is done. Got a couple of variables in there. Step 2, find a formula for the quantity to be maximized or minimized. This is called developing the mathematical model for the problem. And the last little note on step 2 says this step creates another variable that will often require your knowledge of geometry. So yeah, the thing I want to try to make really big is the amount of area inside that pen. So I need to know a little bit about geometry here. Well, it's just a rectangle, so it's going to be length times width. And at this point, I now have 3 different variables, A, L, and W. And that's a little bit too many variables for the calculus that we're doing. So step 3 says, express the quantity to be maximized or minimized. For us here, it's the A, the area, as a function of only 1 variable, not 2. I don't want to have L's and W's on that right-hand side. And so this step often requires you to find what is called the constraint in the problem. Just barely fit that in there. Now, we do have a constraint in our problem. We can't go and make this area any size we want. There's a limited amount of fence that we've got, right? So it says, oh, with only 168 meters of fence. Okay, so for us, that's our constraint. Okay, great. So if that's the constraint, that there's only 168 meters of fence, it looks like by the time I do 2 widths for my pen plus a length, I have to use exactly 168 meters of fence. What you want to do now is pick one of these letters to isolate. I think L would probably be the easiest, and that would just be 168 minus 2W, 2 widths. Okay, well, I'm now going to take this old formula that I've got for area and I'm going to rewrite it, but I don't want to have L's and W's on that right-hand side. And I don't need to have both variables anymore. I could write it with just 1. I could say, oh, okay, that area would be, here comes my L, 168 minus 2W, multiplied by that last little W there. Okay, great. So that's made things look a little bit nicer. Step 4, this is a step that sometimes it's actually very, very important. Sometimes it's not. It's almost always annoying. It's not super easy to do. And like I said, sometimes it doesn't even matter, but then other times it's really, really critical. So what does it say here? Find the interval of possible values for this variable that you're playing with. For us, it's the W, the width, from the physical restrictions in the problem. This is not always an easy task to go and find this interval. Okay, so this is going to be the interval in our case for W, because that's what I see over on the right-hand side. So what is the very biggest and very smallest that the W can be? Now, this is not necessarily going to make a good pen for putting cattle in, but we just have to find like the upper and lower limits for those values. As I look at this story, the smallest value that W could take on would actually be 0. Now, again, it's not a smart way to fence off some cattle, because you'd have like no width and then just a really long fence, 168 meters, and then no width there again. So yeah, horrible for trying to get a good area, but it technically is possible. So we've got 0 on the low end, less than or equal to W. Now, what's the biggest it could be? Well, if you took your fence and just went all the way out with half your fence and then all the way back with half your fence and had no L, that's kind of the upper limit on how big that W could be. And that would be half of your fence. So that would be, in this case, 84. So it looks like we have to have a W that's somewhere inside that interval. And in this case, the interval's closed, right? We could do it like this with closed brackets, right? And we can say, oh, okay, great. The W has to be somewhere inside those endpoints. Here's why that's important. I'm going to go way back to like page 4 when we were doing our notes. And we talked about the extreme value theorem. And we said that if you take a look at a function, and if it happens to be on a closed interval, like right here, if that's where you're looking, then there will be an absolute maximum or minimum. If the interval's not fully closed, like these ones, well, then sometimes there isn't a max or a min. But if it is closed, it's there. And it might be one of these flat spots on the graph that the calculus can find, or it might be one of the endpoints. But the maximum and minimum value of the function is there to be found in cases where we've got a nice closed interval. So that's kind of good news that we've actually got this interval that only goes from 0 to 84 with hard edges on it, because I know that somewhere in there is a best answer. And it might even be when the W is 0 or when the W is 84. Okay, step 5. Here comes the calculus. Use calculus techniques to obtain the absolute maximum or minimum. We're basically going to be looking for critical points. Okay, that's going to be our main plan, is to look for them. And we might check the endpoints as well, right, if this thing is a nice closed interval. So endpoints are definitely worth checking. So this is going to be a lot faster than completing the square was back in Math 11 for parabolas. Here we're going to say, okay, that function A, if I take what's up here and just distribute the W, I'm going to have negative 2W squared plus 168W. All right, going to do a derivative. Going to do a dA dW and just see what I get. Okay, well, when I try that out, I end up with negative 4W plus 168. Okay, so why are we doing this, right? What's the point in doing this derivative and setting it, possibly equal to 0, or maybe it does not exist? The whole idea is that in your mind, you have to imagine that there's this graph of how much area can I get versus my choice that I choose for W in this case. And for this particular story, somewhere in there is this perfect amount where if you choose just the right W, you're going to hit the peak on that graph. And what's special about that peak is that the derivative for that function is 0, right? That's how maximums and minimums work. It's going to be some sort of critical point. It could be a place where the derivative does not exist, but it's definitely going to be a critical point. So we're just going to go and take a look and say, okay, could this thing, this derivative we've just found, could it either be 0 or does not exist? And that should catch one of those flat spots, one of those interesting points. And yes, we can make that derivative equal to 0 if the W is equal to 42. You can't break this thing. It's just a nice polynomial. All right, thinking back to that extreme value theorem, sometimes you'll end up finding the best solution at an endpoint, and sometimes it'll be at a critical point. So we're now going to try out all the possible values. We should go and check the W of 0. That was the first endpoint. Then we're going to check a W of 42. That was the critical point that we found right here. Then we're going to go and check the W of 84. That was the other endpoint. Somewhere in there is the best story. And so you're like, okay, let's give this a try. How much area is there if I put 0 in for W, thinking of A as a function of W? And when I tried that out, just putting that back into this original equation up here, I ended up with no area at all. That's a pretty small pen. When I put 42 in, I found an area that was 3,528. And when I put a W of 84 in, I found an area that was also 0 again. Okay, well, it doesn't take too much effort now to figure out where the best story is. If you're trying to get the maximum area, that would be it right there. And it happens when the W is 42. Now, be a little careful. Go and look and see what they wanted. This one wants a lot. It wants to know the largest area. That's this request right here. And then what are the dimensions? And so far we only know W, we don't know L. But we could go back to this constraint right here. And if we know that W is equal to 42, if we substitute that back in, we can see that the L ends up actually being 84. So we're ready now to answer all the questions. Okay, it's the best area. Ends up being 3,528 meters squared. And the dimensions, they end up being a width of 42 and then a length of 84. And I just went and substituted that 42 back into the constraint to figure out what that L would be. So that's the plan. Not every single one of these stories is going to use all 5 steps, but we're going to try to do those steps. You know, sometimes there won't be a graph. Sometimes there will be. We're going to do 3 more here for this lesson. So here's number 2. It says find 2 numbers whose sum is 20 and whose product is as large as possible. Okay. Well, I can't draw a picture at the beginning for step 1, but I could start laying out some variables. And I could say the first number 1, maybe I'll call that, I don't know, A. Call it whatever variable you want. The second number, because they do talk about there being 2 numbers out there. Number 2, I'm going to call that B. So I'm ready to address these 2 numbers out there. I'm representing them now. And now I'm going to move on to step 2. And it says find a formula for what you're trying to make really big. Well, I want the product to be really big. So I need a new variable for the product. I don't know, maybe I'll call it Y. Y could be the product. And so that would just be A multiplied by B. And right now my objective, right, they're like, hey, try to make that product as big as you can. So I'm kind of thinking, okay, I have to make this thing really big as I can. And I've got a little bit of choice for these values for A and B. I don't have a lot of choice. You know, it's not like I can make A 7 billion and then B 9 trillion. I can't make them really, really big for both of them because it says, oh, they have to add up to 20. Okay, well, step 3 says try to get it down to just one variable on the right-hand side. Use that constraint. And there definitely is a constraint in this problem. They have said that the 2 numbers A and B add to 20. I'm going to use that constraint, that little math fact, that equation, to write one variable in terms of the others. It doesn't matter which one I pick. You know, maybe I could say, oh, well then A is just 20 minus B. And now I'm going to rewrite that story about the product. You know, a second ago, Y was equal to A times B, but that's too many variables on the right-hand side. But I could write it like this. I could go 20 minus B times B. Okay, well now I've only got one variable over there on that right-hand side. I could even, if I chose, write it like this. Negative B squared plus 20B. So awesome, I have just the one variable to think about. Now the next step. Not always the easiest step to accomplish, but we need to think about the interval. We've got one variable left over on that right-hand side. It's B. So what is the interval for B? What numbers are allowed for B? All right, so let me just think about this here. I'm trying to pick numbers off of a number line. So I'm just going to get my number line set up. All right, so I've got 0, 10, 20, and so on. And you might think, well, the numbers have to be between 0 and 20. You know, like maybe it could be like 5 and 15, maybe 10 and 10, maybe 11 and 9. But actually, there's nothing that says that one of the numbers, like b, that it might even be 21. And you might think, well, no, they have to add to 20. Well, one of them could be 21. The other one could be -1. It didn't say that they couldn't do that. So actually, it turns out I don't right now have any limit. It didn't say they had to be positive numbers. So in terms of choice for b, we're wide open here. We could actually play with any number anywhere for b. We just have to be a little bit careful what the value would need to be for a to get them to add to 20. So the interval for b, it's actually -infinity to infinity. Now that's a little more troubling than having a nice closed interval, because if there's a closed interval, I know there's going to be a best solution, and it might be at an endpoint, but I know there's going to be a best solution. But with this, it looks like we have no endpoints. So we have to think a little bit more with our problem. We can't just go and grab the critical points and the endpoints and check them all. We might have to do a little more thinking to make sure we've actually found a nice maximum. Okay, well, here we go. We know that the function we're trying to maximize, when you write it in terms of just one variable, looks like this. And b can be anything from -infinity to infinity. So let's do a derivative and see what the calculus has to offer. And it gives us -2b plus 20. And I'm kind of wondering, are there any critical points out there? Can I make that 0, or can I bust it? Well, I can't break it because it's just a nice polynomial. But there is a way for me to make that equal to 0. And that's if b is equal to 10. Now you have to be a little bit careful here. You have to convince yourself that b being 10 is actually a really good idea. I don't want to find a minimum, right? I want to make sure I've got a maximum. So you start thinking about, well, what's this derivative going to do when I put in numbers that are a little bit above or a little bit below 10? Like if I put 9 in for b, just putting a 9 in my mind right here, I would have -2 times 9 is -18, add 20, that's a +2. So I have a positive derivative before I get to 10. What about at 11? -22, add 20, -2. Oh, I've got a negative derivative later. Okay, so I'm convinced that we're on the right track. The story is going to actually look kind of like this. We've got our choice for b going on here, and then y, this is the product. And it looks like we have found a nice flat spot on the graph when you get to 10 for b, and we have a positive derivative before that, always positive, like always was, and then a negative derivative later. I think this is great. I think we have found the best choice right up there at the top. The calculus has offered it to us. I had to just kind of double check to make sure that this was on track here, not going to be a minimum. But I think we're good. I think we can write down what the answers are here now. Okay, here are my two numbers. One of them is b, and it's going to be 10. And then I can go and back up to my constraint here and say, oh, okay, well, if I put 10 in for b, 20 minus 10 is another 10. Oh, they're both 10. Okay, so the two numbers, it looks like b is equal to 10 and a is equal to 10. And that gives you a pretty decent product, right? Multiply them together, you get 100. And if you try other combinations, like 9 and 11, well, it's close, 99, but it's not as good as 100. If you go with, I don't know, 5 and 15, what do you get, 75, right? Not as good as the 100. So the two numbers both being 10, that's the best you can do. Okay, let's do two more. Number 3, find the largest rectangle that can be inscribed. In other words, sneak inside a semicircle of radius 2. Okay, I'm just going to play around with this for a little bit, just to kind of show you like what can go right and what can go wrong here, and then we'll settle on drawing something. But if you try to make your rectangle too tall, then it can't end up being very wide, and it may or may not have a lot of area in there. If you try to make it really wide, well, then it can't be very tall, right? It has to be actually quite short. You know, and if you go really wide, like out to here, then this thing is actually going to be very short, right? And it might not have a lot of area to it. So somewhere in there, there's a compromise, right? Between being tall and being wide, right? This might be too tall. It doesn't seem to be very wide. And so I want to find that perfect combination where I've got, a fair bit of width to it, a fair bit of height to it, and it's probably going to be, maybe somewhere around here. And I want to let the calculus actually go and figure this whole thing out. So there's my rectangle, and I'm going to see if I can go and figure out the best way to describe it. It's just sneaking inside that nice semicircle there. In fact, it's got a point on it that's just bumping beautifully into that semicircle. I don't really know right now what that point is. It's got some sort of XY pair to it. Okay, what I do know though is that for circles, they abide by a nice little equation here. They look like this. X squared plus y squared is equal to their radius squared. And in this case, it looks like the radius is a 2. So we have x squared plus y squared is equal to the 2 squared. That would be 4. And I'm going to go and solve for the y. So y squared would be 4 minus x squared. Now, I guess I really should do a plus or minus here, but the minus would just do the bottom part of this semicircle, and I don't really want that at all. I just want the top part. So I'm pretty happy just going with this positive version for the square root of 4 minus x squared. Okay, so that's something I'm going to hang on to, but I think it's time to actually get this thing going here. So I've drawn my picture. That's step one. I'm going to throw some variables down. One of them might be how tall the rectangle is. Well, if I'm going to label that point as xy, then if I think about how tall this rectangle is, it's actually y tall. Now, just here would be x. Let's go all the way back to here. Let's do the whole rectangle. So I guess that would be like an x and another x. So that would be 2x for how wide the rectangle is across the bottom. So I think we're ready to start. Looks like the area of that red rectangle is like length multiplied by width. And I've got too many variables there over on the right hand side. I've got an x and a y, and we don't want to do that multivariable calculus that you might do in your second year of university. So I'm going to say, hey, this equation here for the circle, that's my constraint. That's the thing that ties the x's and the y's together. That's the thing that says, once you make the x's too big, the y's end up being really small. So I'm going to use that as a method to get rid of a variable. And now I can go and rewrite this and say, all right, the area. Here it's just based on your choice for x. I'm going to write that square root just like this if it's okay, just with a 1/2 exponent, because eventually I'm going to do a derivative. Okay. So I want to try to make that as big as I can get it, right? That's my goal. Make this thing here big by choosing just the perfect x value. Okay, well, while we're at it, now's probably a great time to think about the interval. Now that you've got this down to just one variable over on the right-hand side, what is the very biggest and the very smallest that x can be, and still have it make sense in this problem? Well, if x went down as small as 0, basically your rectangle would look like this, right? It would have no width to it and be as tall as it could. Not a great choice. If x went all the way over to 2, then your rectangle would certainly be very wide, but in order to fit inside the circle, it would have to be like totally flat. And those are the two extremes. So in terms of choices for x, we've actually got a closed interval, 0 to 2. It is closed, so that means there is going to be a best answer out there. Maybe the best answer might be with x being 0, maybe a 2, or maybe something the calculus can go and find. But it's definitely time to let the calculus go for a search. So I'm kind of picturing in my mind that there's this graph out there of how much area I can get based on my choice in x. And somewhere in there, there's a peak, and I want to grab that peak where the tangent would be flat. Okay, I'm going to do my derivative. I'll just call it a prime. I'm going to do a derivative with respect to x. Oh, it looks like a product rule. So the derivative of 2x would just be a 2 multiplied by this other factor just left alone. and then add. Then we'll reverse this. Leave the 2x. Now the derivative for this thing, the 1/2 comes down. Leave that binomial just as it is to the negative 1/2. Now multiply by the derivative of that binomial. Ugh, that looks awful. So I'm not too sure how that thing could be 0. So I'm going to start to clean this up here a little bit. Just start rewriting this. Making some changes here. Maybe I'll leave this first part for now just as it is. Now what's happening here? This 2 and that 1/2, they can cancel. There's some x's that get together to become an x squared. There's an extra minus sign. There's a 2 out there. I think we're going to have a minus 2 x squared sitting on top of that binomial. 4 minus x squared, it'll be a 1/2 by the time it's down there. Okay, well that looks awful. I got to get these two terms together, and right now my trouble is this one's just sitting on top of basically a 1. I got to get to a common denominator, and it's looking to me like this thing right here, that is the least common denominator. So we have to get that first term up to that standard, up to that denominator. So it's going to have to get struck top and bottom by that least common denominator. So it's time to start packaging this all over top of one denominator now. I want to leave this minus 2x squared part right here at the back end. That's easy. But what's the other stuff going to do? Well, this thing's going to get hit by that least common denominator. Ooh, they're identical. So when this root hits that root, you'll just have a complete item. You're going to have 2, 4 minus x squared, just like that. Okay, worth tidying. Let's do a little more tidying here. Looks like we have minus 4 x squared plus an 8, all sitting on top of this binomial 4 minus x squared all to the 1/2. Okay, we could factor out a negative 4 in the top. Don't throw it away, just leave it there. We'll have x squared minus a 2, all sitting on top of this denominator. All right, I'm looking for critical points, so I'm wondering, can I make that 0? Can I bust it? And the answer is yes. I can do kind of both of those. I can make it 0 if I make that top 0, and that would mean that x would be plus or minus root 2, you would think, and I'd be tempted to write plus or minus root 2. But if I think about my interval that I had a minute ago, we've already decided that reasonable choices for x are between 0 and 2, including 0 and 2. So I'm not even going to bother putting that negative 1 in. I'm just going to say, yep, positive root 2. And then what could I do here? Well, x could be 2, which I'm going to end up finding because of an endpoint anyways, right? So especially when you've got a nice, beautiful, locked-in interval with hard edges, make sure you check the endpoints. So at this point, I would say, okay, I've got some rectangles to go and check on. How much area do I get if I choose to go with an x value of 0? How much area do I get if I choose to go with an x value of root 2? And how much area do I get if I choose to go with an x value of 2? And I'm going to try all of those out. And what I'm doing right now, I'm not going to check out the derivative. I'm going back up to here, and I'm checking out the actual answer you get for how much area there is based on all of these options for what that x could be. And so I'm just substituting in 0 or root 2 or 2 in for x. And here's what I found. The first time I got nothing, no area at all. That's actually a really, really tall rectangle that's infinitely thin. It's like a straight line up and down. This one ended up with an area of 4, and the last one ended up with an area of 0 again. It's a little flat pancake. And so if you're trying to get a lot of area, it looks like the very best you can do is this story right there. Just looking back, what did they want? At the top of the page there it says find the area of the largest rectangle. Okay, there, we did it. There is your best area sitting right here. It's a 4. They didn't even really want the dimensions. They're just like, yeah, go and get the area. All right, one more to try out. Plywood costs $10 per square meter. Find the least possible cost. So we're looking for a money item, a cost item, for building an open plywood box. Square base, but it has to have a capacity of 32 meters squared. Okay, so square bottom and then some sides. So when you look at the thing, when it's built, it's going to look kind of like this. Just 1 second here, I'm just going to fix my notes. Okay, back again. So this picture, when I look at this box, it has no top to it, but it's got a square base. So it's going to look like that. I don't know what the dimensions of this base are, and I don't know how tall this thing is going to be. Right, there's going to be some height to it. If you take this box and kind of unfold it, just kind of look at all the sides, you've got this bottom, which they're telling us needs to be square, and its dimensions are x by x. And then you've got these 4 sides that stick out. You can kind of imagine them folding up and then getting joined together in order to make the box. And there's no lid. They said it was open. Maybe so you can put toys in there. So if these can flip up and form the side, then this dimension this way is h. Okay, so I've got my picture. Let's start laying down our calculus here. We need some formula for something we're trying to make big or small. Let's go for cost. So the cost is going to be just the area times the price. I've got this bottom, its area would be x squared, and it's $10 per square meter, right? So $10 multiplied by x squared, that's the meterage down there. And then 4 times I'm going to have these sides. I've got 4 of them. So plus 4, $10 for the cost for each square meter. And then the dimensions of those rectangles would be x along the bottom and h up and down. Okay, just tidying that up, just kind of packaging it here. The cost would be 10 x squared plus 40 xh. Okay, so here's what's going through my mind as I look at this right now. I'm going to try to make this as small as I can, right? Looking for a minimum. And I'm a little bit annoyed because right now I've got 2 variables. This is bad news, right? To have 2 variables over here on that right-hand side. So I've got to get rid of those, or one of those variables. I've got to look for a constraint. So what is it in this story that constrains how x and y are related? Well, we do know that the capacity has to be 32 meters cubed, sorry. So for a rectangular prism like that, the volume would be x squared along the bottom multiplied by height has to be 32. That's just making sure the volume is 32. Okay, let's rearrange that. Let's pick one of those letters and isolate. I'm going to pick h. So if I solve for h, I could say that h would be 32 divided by x squared. All right, here we go. Let's rewrite this cost function. I see it up here. It looks good, but it's got too many variables up there on the right-hand side. Let's write it with just one. So we could say, okay, your cost would be 10 x squared, that pays for the bottom, plus 40 times x times, now instead of writing an h, let's write this 32 divided by x squared. Okay, tidying that up a little bit, This is 10. I'll write it down underneath. We can talk about the interval. So the cost is 10 x squared. Now 40 times 32 is a big number, 1,280. And there's one x left in the bottom. I'm just going to write that as x to the negative 1. Okay, there's my cost function. Time to consider the interval. This is never fun, but something we should think about. What are the range values here for x? What is the smallest and the biggest it could be? Well, you could make that bottom very, very small. It'll have to be a super tall box in order to have enough room for 32 cubic meters, but there's really no limit on how small you can make it. You just can't quite make it 0. So I'm going to put a soft edge on that 0. And you actually can make the box super wide. You could make it 80 meters by 80 meters. It would be very expensive, but you could make it 80 by 80 meters as long as you made it super short, this overall box you're making. So in fact, why stop at 80? You could make it as big as you want on the base, but you will have to make it very short. So the interval is actually soft edges both sides. We're going to go from 0 to infinity. So this is the interval for x, right? What are your choices for x? Well, they got to fit in there. Okay. Hopefully the calculus can find the answer, because it doesn't look like it's going to be an endpoint issue. So, taking a derivative, you can write c prime, or if you want to, you can say, hey, how about a dc dx? Be explicitly clear on what we're doing with our derivative. Okay, well, taking a derivative, that would be 20x. The minus sign comes down, minus 1, 2, 8, 0, x to the negative 2. Okay. Well, I can't really imagine when that's equal to 0 very easily, so I'm going to rewrite this a bit. That's like 20x minus 1,280, all on top of an x squared. Right now, this 20x is just sitting on top of a 1. So I'm going to rewrite that. Let's go for a common denominator here. dc dx. I'm going to sit on top of x squared. See what it looks like. Multiplying by x squared, I'm going to have 20x cubed minus 1,280. No, that actually factors. We could write dc dx is equal to, pull a 20 out. We're going to have an x cubed minus a 64, all sitting on top of an x squared. All right, now I'm wondering, calculus, what do you got? Sorry, let's put this right side up here. Got any ways to make that 0? Got any ways to make that does not exist? Yeah, I can make it 0. If I go with the cube root of 64, and the cube root of 64 is actually just a 4. Okay, so x equals 4 is interesting. And for this one, I'm tempted right away to go, hey, x is equal to 0. But you know what? Looking at our interval, just back up here, we actually said that the x's have to be a little bit bigger than 0. So technically, this is never quite going to happen. So the calculus is just coming back with one answer, this idea of x being 4. Now, a little analysis here in our heads, even without a graphing calculator. We can start to think about what this story is going to look like. There's something interesting happening at 4 for x. We've got our cost going on here. And it turns out the cost, when you get near, looking back at this function, when you get near x is equal to 0, this is going to explode and go way up as an asymptote. And then when x's get really big, this is the dominant term and it looks like a parabola. So you've actually got some sort of cost function that goes way up high here, comes down to a minimum at 4, and then kind of goes like that on the other side. So yeah, I think this is going to be good. I think this will be a minimum. Another thing you could check is that this derivative, if you put numbers in that are just less than 4, you'll see that you've actually got a negative derivative, and when the numbers are bigger than 4, you've got a positive derivative. So we are finding a minimum. So this is good. We're finding the right spot. The only thing they did want to know, they did say, go and find the cost. They didn't even care about the dimensions. They wanted the cost. So now you'd have to go take that magical 4 value, put it into your cost function, right? So in goes this 4, and find out what the cost would be for a plywood box with 4 meters by 4 meters along the bottom. So I'm going back to the original machine. I'm going back to this one. I'm going to put my 4 in there to see how expensive it is. And it is expensive. It ends up being $480, but you can't do better than that. That's the lowest you can get the cost for this box if you want it to hold 32 meters cubed in it. So kind of looking at this thing big picture, we establish what it is that we're trying to make big or small. Usually there are too many variables on the right hand side, so you look and say, okay, well, can I get rid of a variable somehow based on a constraint? And once you've gotten rid of a variable, now all of a sudden this thing that you're trying to make big or small only has one variable in it. And so then you say, all right, calculus, you're up. Try to find me a flat spot here, right, where the tangent would be nice and horizontal. And then this time it said, oh yeah, that's going to be when that x value is 4. And then just double check in the end that you're actually giving the answer that they wanted. Here was the cost. And that's going to finish up our first video. And in the next couple of lessons, first video on max min, and the next couple of lessons are going to be just some more examples of max min.